Alright guys, Andy Staines here. We can talk a little bit about circuits and energy. So to talk about circuits and energy, we need to use some terminology to identify the different values and the different bits and pieces within our circuit. So I've got some terms outlined here. And these are the key terms that we're going to be looking at. There's lots of others to cover, but these are going to be our starting point. So we're measuring energy. So we use a capital E to represent energy. It's measured in the joule. Capital J is the unit of measurement of is the shorthand for the unit of measurement, joules. So if you see 18J, that means 18 joules. Okay. Power, capital P for power, measured in the watt. Okay. Capital W stands for watts when you're looking at the value. Time. Small t for time, measured in seconds, and we use a small s. It's important to remember that in engineering and physics and electrical design, that time is always measured in a second. So if you get time in any other format, you've got to convert it to seconds before you can use it. Q stands for quantity of electrical charge, and it's measured in the coulomb with a capital C. That's our unit of measurement, shorthand. V stands for voltage or electrical potential, measured in the volts. Okay, got capital V. Now we always measure in the volt, so we always use a V as the unit symbol, but you may use the other letters to describe voltage or potential. You might even see it described as electromotive force. So just be aware, you could see a U, or you could even see a capital E, which is confusing because we've got an E up here, but I'm going to stick to V when we're dealing with DC volts, which is what we're going to talk about in this short explanation. Finally, I've got I, which represents current in amperes, and that is our capital A, which is the unit symbol. So just to outline, the letters down the left-hand side are what we put in our equations to represent these various terms. The letters down the right-hand side are the unit symbol that goes after the value. If you want to write down 6 seconds rather than write seconds, we just write 6s, etc., etc. So you might want to pause here and just make a little note of these bits and pieces, just to make sure that you're happy with all of those. Before we move on to the next. So we've got some equations. So we're just looking at 3 simple equations today. That's all we're going to deal with. So E equals PT, which means energy equals power times time. No time symbol in between P and T. We are just as an assumption in maths that when you have 2 letters side by side, that means they are multiplied. You might sometimes see a dot in between. Okay, so the dot is going to represent multiply. That's quite often the case. You might see that on some American or even British videos, etc. I'm not going to use that shorthand. Okay, so we're just going to have this E equals PT and Q equals IT and P equals IV. Now on the other side here, we've got some transpositions of those formulas again. This is something you need to be able to learn how to do to make those transpositions if you're going to be successful in exams and also successful in the field as a practicing electrician. But to help you out, I've just written out some of those transpositions. Again, I'd take the time to make a note of these, the key formulas as they are standardly stated, and then those transpositions. Okay, now the standard format you can see there, it's all in a line, it's all nice and straightforward. The transpositions are all, well, we've got kind of fractions going on here. So I always find it easier just to remember the simple version like this, and then learn the technique to transpose, and you can work out all the others as we go along. So again, if you want to pause at this point, make a little note. I think you might find that useful. So I'm just going to again just lose these, okay, before we move on to talk about our circuit. So I'm going to draw a very simple circuit. This circuit has a source of electrical energy In this case, we're going to have, oh dear, that's awful. We're going to have a cell. So our cell is going to be providing us with our source of electrical energy, and it's going to be connected into our simple circuit. It consists of a switch and a load, and the load in this case is going to be as simple a load as possible, which is simply a resistor. I'm not going to worry about the value of the resistor at the moment. Here's our cell with a plus and a negative, and that's our source of electrical energy. Switch is our means of control, and our R is the point at which the energy is dissipated into the circuit. So an electrical circuit will move energy from a source through a means of control, and the energy will then do work. So energy, E, equals work done. Okay, less efficiency, but that's a key point here. Energy and work done are pretty much equivalent without worrying too much about the efficiencies of the system involved. But here we have energy stored in our battery, and that is chemical potential in our cell, chemical potential energy, and our resistor, as current flows through it, it's going to get hot. Okay, so that heat is going to be dissipated off by our resistor. Okay, and that is our resistor doing work. Okay, we might actually be physically using the resistor to do some useful work. It could be a heater, for instance. So that's our simple circuit. Well, let's add some other little values in there, just to make this nice and easy. Okay, let's say that our source of energy, V, okay, our electrical potential is 10 volts. Okay. Now let's say that this resistor, our heating element, has got a wattage. And we're going to say our wattage is, our power rating is 50 watts. Okay, so we've got some useful information there about the voltage and about the power dissipated by our resistor when it's connected to a 10 volt supply. Then we've got a switch. Now let's say that we operate that switch for 100 seconds. So we apply 10 volts to a resistor. Power rating of this heating element at 10 volts is 50 watts. And we operate that for 100 seconds. So we're going to take that information and just see what's happening in the circuit in terms of energy transfer, current flow, quantity of charge, etc. So let's just turn this off for a moment and look at these values. So I'm just going to write those out again. V equals 10 volts, P equals 50 watts, T equals 100 seconds. So what can we do with that? What can we find out? Well, what don't we know? We don't know what current is. We don't know what the quantity of charge dissipated within the circuit is, and we don't know what the energy in the circuit is whilst it's operated for that period of time. So first of all, I'm going to ask you to go back, pause the video right at this moment, go back, have a look through the formulas, see if you can work out which formulas you can use given the information we have here, and see if we can come up with some answers for current in amperes, quantity of charge in coulombs, and energy in joules. How many amps, how many coulombs, how many joules, given these values down the side. So off you go, and when you've come back, play the video again and I'll give you an explanation. Okay, so let's first of all have a look at the current in the circuit. Now, important thing to remember is we're going to need to do some transposition of formulas. So we know that power is equal to current times voltage. We need to get the current on its own. We need to remove voltage. So we need to do some formula manipulation here. Now, at the moment, current is multiplied by voltage. If I go into the formula and I divide this side by voltage, I'm going to cancel out volts. Volts over volts cancel out, or it becomes 1 effectively. Now, one of the most important rules in formulas is that whatever we do to one side, we must do to the other. So I'm going to divide the other side by volts. Now, our formula looks a little like this. P over V equals I. Let's twiddle it round and say that I equals P over V. Let's put the numbers in. 3 little dots, which means therefore. Therefore, I is equal to 50 watts over 10 volts. Therefore, I equals 5 amperes. Number 1. Job done. Okay. Now we're going to move on to having a little look at the quantity of charge in this circuit. So, quantity of charge is equal to I times T. Now we know I now. We know that I is 5 amperes. We know that T is 100 seconds. So we don't need to do any transposition here. We just know that Q is equal to 5 amperes times 100 seconds. So Q is 500 coulombs. Brilliant. That was nice and easy. Okay, next and last point. We know that energy is equal to power times time. Again, simple this one. No transposition. Energy is equal to 50 watts times, again, 100 seconds. So our energy here is 50 times 100, which is 5,000 joules. Okay, well, I'm hoping that you were able to get the same answers coming up. And if we go back to our circuit, we can actually add in those bits and pieces into our circuit. I seem to have lost a little bit of our circuit there. Let's put that back. So we have I equals 5 amperes. We have energy at this side. Energy supplied is 5,000 joules, and then the work done, of course, is also 5,000 joules. We're ignoring any losses, like the wires will get hot, but it's probably, in this case, it's not particularly significant. So we're talking about energy in on one side, energy out on the other side. Remember, energy cannot be created or destroyed. It only changes from chemical potential energy within our battery to electrical energy in our circuit through to heat energy at our resistor. That's the energy doing work. And finally, we also know that the quantity of charge, so think about our electrons in here. Okay, lots of electrons within our battery. They are wanting to get away from the negative. Remember, electrons flow away from negative towards positive because they have a negative charge. So the electrons are all moving around the circuit. The quantity of charge, measured in coulombs, Q, was, what was it, guys? It was 5 amps times 100 seconds. So we're talking about 500 coulombs. Now, just to put that in context, 1 coulomb equals 6.24 times 10 to the 18 electrons. That's a lot of electrons. There we go. First starter on quantity of charge, energy, voltage, power and current in circuits. I hope you found this useful.